This video is mostly about a graphical approach to differentiable functions. What makes a function have a derivative or not, mostly from a graphical perspective, though we will do a proof that differentiability implies continuity at the end. Problem 1 says, for the graph of the function f shown below, label the x values for which the function appears to be, not guaranteed because it's just a graph, but appears to be, based on how it's made, part A, not continuous, and part B, not differentiable. Okay, continuity is pretty easy. We've talked about this before. We think graphically in terms of continuity as, can you draw the graph without picking up your writing utensil? Over here you certainly can. We can draw that piece of the graph without picking up our writing utensil, but once we get to this point that is missing, so to speak, that jumps up there to be that point on the graph, -1, 2, then we have to pick up our writing utensil to make that point. That is a point of discontinuity. It appears to be discontinuous there, and it certainly is there. That's pretty obvious. We can draw the graph over here and up here now without picking up our writing utensil, but once we get to 1, then we have to pick it up again. So part A, the answers are, it appears to be not continuous at x equals -1 and x equals +1. X equals -1 and x equals +1. Part B is harder. What does it mean to be not differentiable? When a function is differentiable at a point, what that means is the derivative exists. But what does that mean graphically? One thing it means is that if you've got a discontinuity, you also are not differentiable there. So those same spots where you have a discontinuity, where the graph is not continuous, those are also spots where the function is not differentiable. It does not have a derivative. So we can write those down. But there could be other places. What you want to look for with the other places are, does the graph look locally linear, more and more like a straight line as you zoom in near the point, and is that line not vertical? So you look over this graph, generally speaking, it looks smooth. Over here it looks smooth. Any point I look at, it looks like it's got a well-defined tangent line. It looks like if I zoom in near any point, it will look more and more like a straight line. Of course, at the points of discontinuity, it won't. So those are places where you are not differentiable. There is a spot right here, though, where there's a corner in the graph, you might say, or a cusp. The graph is straight here with a slope around -2 or so, coming down to the point there. But then after that point, or as you let x approach 0 from the right, the graph has a positive slope. So there's some sort of corner here at x equals 0. That is a place where the function appears to be not differentiable. Okay, and again, we're going on appears to be. We're going to see in the next problem that appearances can sometimes be deceiving, so you have to be careful. But again, this is purely graphical, and we are describing it in terms of appears to be. There is one other spot where this function is not differentiable based on something I said a minute ago. You want to look for a smooth graph. You want to look for the function to be locally linear, look more and more like a straight line as you zoom in closer and closer to the points. However, you do not want that line to be a vertical line. You want it to have a non-infinite slope. You don't want it to have an infinite slope. And at this point, right about there, it looks like the tangent line, which would exist, is vertical, infinite slope. You don't want that for the function to be differentiable. In other words, it's not differentiable at this value of x. It appears not differentiable at x equals 2. And if you were asked to give a reason, you would say because it looks like the tangent line at this point is vertical. A particular example of a function with a formula where that kind of thing happens, this is a separate calculation here, is the cube root function, cube root of x, which is the same as x to the 1/3 power. When we are plugging in real values for x, it turns out the graph looks like this over here when x is positive and this over here when x is negative. It is an odd function. It's got a vertical tangent at 0, and it fails to be differentiable at 0. I do have a video, by the way, I'll put a link to it here in the upper right corner, where I prove that using a limit calculation, that it's not differentiable at 0. In problems 2 and 3, we're going to use technology. Part A says, let f of x be the absolute value of x. Decide, don't prove, but decide based on technology whether f is differentiable at x equals 0, you might say appears to be differentiable or not, by zooming in toward that point, x equals 0, and also y equals 0, since the absolute value of 0 is 0, with a calculator. Let's do that first. And then we'll just write the answer. You may know already that on a wide enough window, the graph of the absolute value function does look like a V, you might say. It does look like it appears to have a corner at x equals 0. Another way to see that is to realize the absolute value of x is the same as this piecewise function. It equals x if x is greater than or equal to 0, and it equals the opposite of x. You could call it negative x if x is less than 0, but realize when x is negative, like negative 5 for example, negative of negative 5 is actually positive 5. So this is actually a positive quantity here. So you might suspect that this is not differentiable at 0. Let's try to confirm that with a graphing calculator. So we need the absolute value function. We need to do, I'll go to the catalog here, ABS, it's right there right away, of x. There is the absolute value of x. We'll start with the window that you see here, negative 5 to 5 in both the x and y directions. Graph it. It looks like a V. Like we said, it looks like it's not differentiable at 0. Let's change the window. Let's zoom in. We'll go negative 0.5 to positive 0.5 in both the x and y directions. You do want to, technically speaking, zoom in the same amount or by the same factor in the x and y directions. Otherwise, it can be deceiving. Still looks like a V. Let's try one more, and then we'll be satisfied. Let's go negative 0.005 to positive 0.005 in both the x and y directions. It still looks like a V. I mean, that makes sense if you think about the formula. The slope, so to speak, when x is greater than or equal to 0 is 1, and when x is less than 0 is negative 1. And those slopes don't match up at 0. This function is not differentiable. It does not have a derivative at x equals 0. You could say, i.e., f prime of 0 does not exist. DNE means does not exist, okay? Part B, the function is f of x equals the square root of x squared plus 0.0001. You could also use a 1/2 power. Decide whether that's differentiable at x equals 0 by zooming in with a calculator. You may not have any idea what the graph of this looks like. Let's change the window back to negative 5 to 5 to start with in both the x and y directions. Now let's go back to the y equals and type this function in. The square root of x squared plus 0.0001 in the window negative 5 to 5. Here we go. Here's the graph. Hey, that looks like the absolute value function. Is it the same as the absolute value function? Let's try zooming in. Let's go zoom in fairly close right away. Well, okay, let's do the same process we did before. Negative 0.5 to positive 0.5 in both directions. See if it looks any different. Looks pretty much the same, maybe, or maybe there's something funny going on there near 0. Let's try going in further. Negative 0.005 to positive 0.005. What do we see? We don't even see the graph anymore. The f of 0 is not 0. F of 0 is the square root of 0.0001. What would that be? That would be 0.01. Oh, okay. It is above the origin here. Let's change this window to negative 0.05 to positive 0.05. Get rid of 1 0 there. Here comes. What do you know? Still looks kind of like a V, but it does look smoother there than before. Let's go in a bit closer. Negative 0.02 to positive 0.02, say. That's actually a smooth graph. I mean, you might say it's horizontal there. It's actually not exactly horizontal. It just looks horizontal. It's got a horizontal tangent there. It is smooth. It's differentiable. F prime of 0 exists. In fact, f prime of 0 is 0. And in fact, if you know how to take derivatives of these kinds of things, you could take the derivative of this and plug in 0. It does exist. So on a wide enough window, like negative 5 to 5 in both directions, it looks like a V, but we saw that if you go zoom in closer, negative 0.02 to positive 0.02, it looks smooth, kind of like a parabola, though it's not technically a parabola. Why did it look so much like the absolute value function to begin with? Actually, because that's the absolute value function can be defined as the square root of x squared. You can check that out. Try plugging different numbers in for x, and you'll see that these are always equal. And this is very close to the square root of x squared. It just differs by adding this 0.0001 in it. And that's enough to make the corner go away when you zoom in far enough. So this is differentiable. I'll abbreviate differentiable, just diff at x equals 0, i.e. f prime of 0 exists, and in fact, you could prove it equals 0. In problem 3, we're using technology again, but this time with some wild functions. We've actually looked at this first one before. For each of the following functions, decide whether f is differentiable at x equals 0 by zooming in with a calculator, where we're saying it appears to be differentiable or not. Okay, these things again are not proofs. Part A, f of x is sine of 1 over x when x is non-zero and 0 when x equals 0. You can't really type a piecewise function into my kind of calculator, at least as far as I know. But effectively, we can just type in sine of 1 over x and just remember the fact that f of 0 is 0, just to make this defined for all x. So we go to the y equals screen and type in sine of 1 over x. Technically speaking, you should make sure your calculator is in radian mode to get the truly accurate graph that we're after, though the graph would be similar even if it were in degrees. And go ahead and graph it. I picked this window to start with. Let's go ahead and see what this graph looks like. So here it is. And that's kind of strange. Let's zoom in closer. How about negative 1 to 1? Actually, we'll keep the y min and y max the same from now on, and we'll just zoom in the x direction, even though that kind of contradicts what I said to do before. And wow, it's even weirder than it looked at first. Doesn't look like anything nice is going on near 0. Is it calculator error? Let's try negative 0.1 to positive 0.1. Whoa. There is some calculator error going on. You know, the calculator is just plotting points and connecting the dots. This function behaves so wildly that it's actually giving what you might call an inaccurate graph here, though it is sort of getting at the essence of the behavior at the same time. And the essence of the behavior is wild. Whoa, even weirder and weirder as you go in. What's happening here in reality is this function is oscillating in reality infinitely often on any tiny little interval near 0. In fact, no matter how small it is, as long as it contains 0 in the middle, the oscillations will occur infinitely often. Why? Because as x goes to 0, say from the right, 1 over x goes to infinity, and the sign is going to go through infinitely many oscillations between negative 1 and 1. It's not just infinitely many oscillations, it's infinitely many oscillations with an amplitude that stays at 1, though you can't quite tell that because the calculator is doing such a bad job really in graphing this in reality. Let's just try one more here. Yeah, it's just doing a bad job, but it is hinting at the fact that it's wild and it is oscillating infinitely often in reality. So definitely not even continuous at 0, also not differentiable at 0. Doesn't look more and more like a straight line with a non-infinite slope as you zoom in near the point. All right, well, okay, that's part A is not differentiable. So part A, f prime of 0, does not exist. You could also say that f is not even continuous at 0 because the limit of the function itself does not exist. All right, what about part B? Same kind of function, except I multiplied by x. Talked about the squeeze theorem in a video before. This is going to squeeze the graph toward having a limit at 0, a limit of 0 as x approaches 0 because of the squeeze theorem. But will it look more and more like a straight line with a non-infinite slope as we approach the origin here? Let's go back to a bigger window. Let's try negative 1 to 1. So a little hard to tell what's going on. It looks like there could be a lot of oscillations, but yes, as you approach zero, those oscillations are getting smaller and smaller in amplitude. Let's go ahead and zoom in the same amount in both the x and y directions this time. That would be good to not be deceived about differentiability or lack thereof based on zooming in and seeing if it looks more and more like a straight line with a non-infinite slope. So again, yeah, we are getting infinitely many oscillations. And you might wonder, I mean, those oscillations are getting so small. Is it possible that the derivative does exist? Is it possible it looks more and more like a certain straight line the closer you zoom in near zero? And yes, f of 0 is 0, so it is continuous there. The piecewise definition is making it continuous there. Let's keep going. Let's try negative 0.001 to positive 0.001 in both directions and see what we see. The oscillations get smaller and smaller, but this graph is never looking more and more like a straight line. And if you keep going in near the origin, you might say it looks straight there, real close to the origin, but that's deceiving. That's calculator error. It should look more and more straight on the entire window the closer you zoom in if it's going to be differentiable at 0, and it doesn't. That's enough to say, without proof, doing red here, that f prime of 0 again does not exist. What's the difference? This is supposed to be part C here. What's the difference with part C? Now we're doing x squared. So again, the squeeze theorem could be applied. The limit as x goes to 0 of this function is still going to be 0. The function is going to be between the graphs of x squared and the graph of negative x squared as you approach 0, since sine goes between negative 1 and 1. And it's going to 0 faster than the other one is. Maybe that's enough to make the graph look more and more straight. Let's see what happens. So can I just put that in here, insert the square there? Will that work? Yeah, I think that works. Okay, let's go back to the wider window. Still got to oscillate infinitely often because it's still got the sine of 1 over x there. It's oscillating infinitely often, it turns out, as you approach 0, but you can't really tell. Again, you can say maybe that's just calculator not being so good. Let's zoom in. You're seeing a lot of oscillations there as you're not too far away from 0. But once you get close to 0, it looks pretty flat. But is that deceiving? Is it like the other one? Will we continue to see oscillations like this as we zoom in near the origin at the same rate in both the x and y directions? Let's just see what happens. On this window, we don't see anything. It is graphing it, but it's so close to the x-axis you can't even see it. The graph is looking straight on the entire window the further you zoom in. It is locally linear near the origin. In fact, the x-axis, slope of 0, is the tangent line to this function at 0. So for this part, C here, f prime of 0 does exist and in fact equals 0. This is no proof, but it's plausibility arguments based on the calculator. Does lack of differentiability have any applications? Well, sort of, in the sense that in some applications, non-differentiable functions are what represents reality, or are sometimes even a good modeling tool. In this problem, it's about the acceleration due to gravity. The acceleration due to gravity, little g, varies with height above the surface of the Earth. Wait a minute, I thought little g was constant. Did your teacher tell you little g is constant? 9.8 meters per second squared? Your teacher lied to you. No, okay, they weren't, maybe you say they told a fib. Okay, they were telling you a common approximation to the value of little g. Certainly near the surface of the Earth, within a kilometer or two near the surface of the Earth, little g is effectively constant, okay? But in reality, it's not constant. The higher you go, and you go out into outer space, the little g gets significantly smaller. But if you go down below the surface of the Earth, dig a hole, G varies actually in a different way, according to this piecewise formula. And this piecewise formula is scientifically accurate, okay? Kind of a weird looking formula, no numbers here. Little g is a function of little r. G is a function of little r, where little r is the distance to the center of the Earth, not the distance from the surface of the Earth. Capital R is the radius of the Earth. Capital M is the mass of the Earth. And capital G is called the universal gravitational constant. Whoa, that sounds fancy. If you don't know what the universal gravitational constant is, don't worry about it. It's just a constant. It's related to the fact that according to Newton's laws, at least everything in the universe has a gravitational attraction to everything else that has mass, at least. And it's a constant in that setup. Look at this formula. You use this one, which is a linear function of little r, r to the first power in the numerator, when little r is less than capital R, when you're below the surface of the Earth, when you're underground. And you use a different formula where little r is in the bottom and is being squared if little r is greater than or equal to capital R, if you're on the surface of the Earth, sea level, I suppose, or higher, even way out into outer space, theoretically to the edge of the universe, theoretically, but practically speaking, it won't really have an effect. All right, okay, this is a weird problem. Part A, sketch a graph of little g against r. How in the world are we going to sketch a graph when we don't know what capital G, capital M, and capital R are? Don't worry about it. We're trying to sketch a qualitative graph, you might say. I will give you a little treat here and do an actual computation with a program called Mathematica to show you how this all works out, to give you little g when little r equals capital R. But for the moment, here's part A. Make a graph of little g as a function of r. Again, little r is the distance to the center of the Earth, not the distance from the surface of the Earth. It's a linear function of little r. In fact, you could call it a direct proportionality. It's going to have a graph that goes to the origin and is straight with a positive slope until you get to a value of capital R. It's going to look like that. What is the left-hand limit of this function as little r approaches capital R from the left? You'd use the first formula because that's what's valid when little r is less than capital R. That'll be the limit as little r approaches capital R from the left of this first formula, capital G times capital M times little r over capital R cubed. And you could certainly evaluate that limit for this continuous expression by plugging in little r equals capital R to get capital G times capital M times capital R over capital R cubed. And then you could cancel that capital R with one of those. And this simplifies to capital G times capital M over capital R squared. And that'll be that left-hand limit. We might then wonder what the right-hand limit as little r approaches capital R is, and that will tell us whether little g is continuous or not. We'll get there. In fact, maybe we should do that right now, actually, and that'll help us finish the graph as well. So we're going to also do part B now. We're sort of doing part B here. We're thinking about the left-hand limit. What is the right-hand limit as little r approaches capital R from the right? We need to use the second formula here because that's what's valid when r is greater than little r is greater than capital R. So we go ahead and plug in that formula, capital G times capital M over little r squared. That expression in and of itself is a continuous function of little r. You can evaluate the limit by plugging in little r equals capital R, and lo and behold, you get the same thing. And lo and behold, this is also the function value at capital R. The left and right-hand limits are the same. They're equal to each other. The two-sided limit exists and also equals the function value when you plug in little r equals capital R. And this, like I said, is equal, therefore, to the two-sided limit. And that means little g is continuous at little r equals capital R. It's certainly continuous when little r is less than capital R. It's also continuous, that's a continuous function of little r, when little r is greater than or equal to capital R. The right-hand limit's got to be the same. And this is not a linear function. It's something over r squared. It's a nonlinear function that's going to have the horizontal axis as a horizontal asymptote. So the graph looks like this. The value of the function at little r equals capital R is this limiting value, capital G times capital M over capital R squared. Before we do part C, let me do my little treat for you here. Use this computer program called Mathematica to show you that I plugged in the values of capital G, the universal gravitational constant, capital R, the radius of the Earth, capital M, the mass of the Earth. The radius has to be in meters, because remember, little g, we want units that are meters per second squared in the end. M has to be, the mass has to be in kilograms, actually, not grams. Capital G, I forget its units. It involves meters and kilograms, and I think it involves newtons and seconds in some fancy way. It's a very small constant. You can see 10 to the negative 11 power here. Anyway, if you enter these numbers into Mathematica and then compute capital G times capital M over capital R squared, lo and behold, you get about 9.8. How about that? Isn't that amazing? The value you're used to for little g near the surface of the Earth. As far as answering part C goes, we just did part B and said yes, little g is continuous function of R. Is it a differentiable function of R? Overall, the answer is no. Look at the corner. No, because f prime of capital R at least appears to not exist. Does not exist. Okay? It is differentiable everywhere else. The derivative exists when little r is strictly less than capital R or when little r is strictly bigger than capital R. But it appears at least that capital R, f prime of capital R does not exist. Could you prove it? Yeah, it's not too hard. I mean, you could do a limit calculation based on the definition of the derivative. The left and right hand limits would be different. I won't go through the details. I would encourage you to do that as an exercise. In the last problem, we do a proof that differentiability implies continuity. And that would also mean if a function is not continuous at a point, it can't be differentiable there, because if it were differentiable, it would be continuous. That logic is solid. The problem says, suppose f is a function defined on some open interval near x equals c, some little interval, say centered at c. Open interval, you do not want c to be an endpoint. So we can focus on two-sided limits and not worry about subtle details of one-sided limits. Suppose that you know f is differentiable at c. The goal is to prove that f is continuous at c. Before we do the proof, let's think about what we would need to prove. What does it mean to be continuous at c? It means, we've talked about this before, the limit as x approaches c, the two-sided limit, which I can compute because I'm talking about this function being defined in an open interval near c, of f of x should equal the function value there. We've talked about that in this video, and we've talked about it in other videos. The key to doing this problem, a partial key to doing this problem, is to realize that this would be equivalent to saying that the limit as x approaches c of f of x, that limit minus the function value would be 0. And f of c is a constant. Okay, c is a particular number. Here, x is a variable. I'm letting x approach c. Being a constant, this f of c could be thought of as the limit as x approaches c of f of c, because f of c is a constant. There's no x in there. And by a property of limits, the limit of this function minus the limit of this constant function is the limit of the difference. So this is one key insight, a trick you might say, to realizing to prove continuity. Yes, we need to prove that, but it's equivalent to showing this limit is 0. Another key insight you need is you need to use the fact that f is differentiable at x equals c. The derivative f prime of c exists. And that's based on a limit as well. That's the limit definition of the derivative. So let's see if we can't write the proof out by thinking about using those ideas. It probably takes some scratch work, some trial and error to really figure out this proof from scratch, and I don't want to make this video go too long, so I'm not going to do that scratch work. But here's the key thing. Okay, technically speaking, proof should be written in sentences. I'm not going to write sentences, so I'm just going to call this the idea of the proof. But you could certainly, based on what I say, fill in sentences. I'm essentially just going to do a calculation. I'm going to calculate this limit. But how can I calculate the limit if I don't know what f of x is? I'm trying to show it equals 0. I don't know what f of x is. How can I possibly calculate it? You got to use the differentiability. How can we use that? F prime of c exists. Oftentimes you use this form of the definition of the derivative. This limit must exist. That's what this means. That's equivalent to another limit existing. It's equivalent to the limit as x approaches c of f of x minus f of c divided by x minus c existing. Why? Why are these limits equivalent? Effectively, to get from this limit to this limit, you just let h equal x minus c, or equivalently, x equal c plus h. You replace c plus h with x here, replace the h with x minus c here. It's really the same limit. If x equals c plus h and h is going to 0, then x is going to c. And so we write x goes to c. It's still the limit of a bunch of secant lines to give you, by definition, the slope of the tangent line. It's the limit of slopes of secant lines by definition that gives you the slope of the tangent line. We got to use that. We got an f of x minus f of c here. How do we get the x minus c down there? Do mathematicians' favorite trick. Either add 0 in a convenient way or multiply by 1 in a convenient way. In this case, we're going to multiply by 1 in a convenient way. We're going to divide by x minus c, and we are going to multiply by x minus c. Okay? That doesn't change the function as long as we're not dividing by 0. But remember, with limits, it doesn't technically matter what happens at x equals c in this case. It doesn't matter that we're dividing by 0. Now, technically speaking, in this next step, you really should write in sentences to explain this step, because I'm implicitly assuming the limit exists in writing what I'm writing here right now. I'm assuming both of these limits exist. And they do. The limit as x approaches c of x minus c is c minus c is 0. And the limit as x approaches c of this thing, well, that's the derivative. That's f prime of c. These limits do exist, and that allows you to justify this limit of this product being the product of these limits. And then, yes, this is f prime of c times 0, but f prime of c times 0 is 0. We're done. QED. Okay, with the idea of the proof, again, you'd want to write sentences. You'd want to say things like, okay, you'd want to say things like what we're trying to do. We would be trying to show this limit is 0 because this is the definition of continuity. You'd want to justify this step by first saying that this limit exists and this limit exists. This one's f prime of c, this one's 0. Therefore, this limit of this product is the product of the individual limits. That one's we know is f prime of c. This one we can easily compute to be 0. This limit is 0, and that means we're done. That means f is continuous at c. Thanks for watching.